You are welcome to today's session of our course in actuarial statistics. We started with the topic of interest theory. We want to continue and finish up with interest theory. So last week we covered simple and compound interest. We looked at frequency of compounding. We looked at effective rates of interest. And we looked at rates of discounts. So today we want to look at force of interest, present value and future value, equation of value, and then we look at an exercise. Let's move right into the lecture for today. Introduction to force of interest. Let's know what force of interest means. The force of interest, in this case, we are using the Greek symbol delta of T to represent force of interest. So the force of interest, delta T, is the instantaneous rate of increase of the accumulated amount as a percentage of the accumulated amount at time t. If you remember, we spoke about accumulated amounts in our class last week, and we are saying that this force of interest is trying to describe that infinitesimal change, all right, that small change. We want to see how a very small change as compared to the current, that's a very small instantaneous rate of increase of the accumulated amount. So that's very small change in the accumulated amount as compared to the current accumulated amount. We want to compare them, okay? So if I say that small change, this is representing that small change in the accumulated amount, all right? And then this represents the current accumulated amount. So small change in 80, right? So the force of interest is very important, especially when you are dealing with continuous compounding. In our previous lesson, we considered a case where you are earning interest, for example, every year, or if it's a nominal case, let's say it's being compounded twice in a year, you are earning interest at the end of every 6 months. In the case of continuous compounding, you are earning interest all the time. It's continuous. So you do not wait for the end of the year before you earn interest. You earn interest continuously as the clock is ticking. You are earning interest. So it is a continuous compounding concept and represents the limits of the effective rate of interest over infinitesimally small periods. So because it is working with continuous compounding, the interest here is when there is that little change in time, by how much has our investments increased, okay? When there's that very, 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 very small change in time, what has happened to our investment? So it's almost close to saying that right now, at this time T, what is happening to our investment? The general formula for force of interest calculation is this: delta T equals the first derivative of the accumulated function, or in this case, the accumulated amount, all over the current accumulated amount. We are using 80 to represent the accumulated amount instead of capital 80 because we are assuming that the principal invested is just one. So we want to look at the derivation, how to derive the force of interest. So let's consider this two. This is time t, and this is time t plus change in t. Now this change in t is a very, very small change in t, okay? So what is the interest over this period? What is the interest or the rate of interest over the period t from time t to time t plus change in t? If I use a timeline, here may be t, and then very, very, very small time, maybe t plus that small change in t, okay? So this is time t, and the next moment is time t plus change in t. So we want to know what is the effective rate of interest over this period, okay? Now we are equating this to be equal to that change, that is the change in accumulated amount from 80. This is the accumulated amount at time AT. And then this is the accumulated amount at time T plus change in T. So the difference is the value that has accumulated, that is the change of the value that has occurred over the current accumulated amount. Okay, right. So this is where we start from. Then we'll take the limits of this function. Okay, so using differentials and first principle issues, if you remember, delta t is now going to be equal to the limit of the as change in t approaches 0 of this function all over change in t. Now, if this is the case, we know that then the numerator here is equal to all this. So I'm going to fix everything here, all right? That's how come I'm able to get my 1 over AT out. Then I now have the limit as change in t approaches 0 of this entire function, okay? So what happened here was that you see this thing here is the same here and it's equal to this, okay? So we are going to fix the whole of this in the place of this, all right? When we do that, you realize that, well, you can bring out, because the limit is respect to change in t, it has nothing to do with this. So you can bring it out. That's how come we had 1 over AT here times the limits as change in t approaches 0 of whatever is left. So what is left is what we have here. I've already brought out 1 over AT. So I have this one left. But remember, I divided by change in t. So I have to bring my change in t here. Okay. Now this then is equal to I have my 1 over AT here. So that's what I have in the denominator here. And then this entire thing is the first differential of AT by first principle. Okay. So we interpret delta t as delta t provides a continuous measure of how quickly the investment grows at time t. So now, how is your investment growing now at time t? Okay. What is the relationship between delta t and then AT? This is the expression. This expression gives us the relationship between AT and then delta t. So we say AT is equal to, that is the accumulation function, is equal to the expected value of the integral running from 0 to t of delta s ds. All right. Now, the special case may be where the constant force of interest exists. In that case, it means that your force of interest does not change with respect to change in time. So no matter what time we are referring to, the force of interest remains the same. So we are saying that delta t is equal to delta, where delta is a constant. If that is the case, if we have the constant force of interest, then now the accumulated value AT is equal to e to the power delta t. So take note, when force of interest is not constant, here is the relationship between AT and then delta t. But in the case where force of interest is constant, here is the relationship between AT and delta t. So here's an example. Given that delta is 0.05, this is indicating that it is a constant force because the 0.05 here has no t attached. So no matter what time it is, whether t is 5, t is 10, t is 20, delta will always be equal to 0.05. So given that delta is equal to 0.05, which is a constant force of interest, calculate A2. Okay, so what A2 be? We'll use this formula. A2 is going to be equal to e to the power delta, which is 0.05, times 2, which is replacing t, all right, in the formula. So you can keep this in your calculator and then it gives the value that we have here. Let's look at some examples and applications of the force of interest. Now, we want to look at simple interest and compound interest. How do they play out when it comes to force of interest? If you remember, the accumulation function for simple interest is, all right, when you differentiate this, what do you get? With respect to t, all right, you get r. So using the formula first differential over AT, we have here r which is our first differential, over the function. The accumulation function for compound interest is 1 plus r all to the power t. Okay, so when you differentiate this, you should get ln 1 plus r, sorry. Oh, we should have used r here. I don't want the confusion. Ln 1 plus r, then 1 plus r to the power t. Okay, so we're expecting that is going to be equal to, using the formula, which is the first differential, which is this, okay? So if you want to compare first differential over the function at, this over 1 plus r to the power t. So this cancels out. Then we have ln 1 plus r, which we have here as our delta. So this settles it with simple interest and compound interest. So force of interest for simple interest, as you can see from the formula, it decreases over time. The denominator here is bigger. So you always have this fraction. As time increases, the denominator here becomes bigger and bigger. So it indicates that as time increases, the force of interest also will decrease. But then because under compound interest, delta t is constant, then we will say that force of interest or compound interest remains constant regardless of the time. Now let's compare force of interest for simple interest. Oh, sorry, I think we've done this already. Okay, so there's an example we want to look at. A fund accumulates at a simple interest rate of 5%. Now another fund accumulates at a compound interest rate of 4%. When will their forces of interest be equal? I repeat, a fund accumulates at a simple interest rate of 5%. Another fund accumulates at a compound interest rate of 4%. When will their forces of interest be equal? Now, which fund will have a higher force of interest thereafter? So one fund has this simple interest, another fund has this compound interest. We want to know when their force of interest will be equal. When, which means time, okay? So we're trying to look for that value of t where the force of interest for fund A and the force of interest of fund B are equal. So let's the simple interest one be fund A and compound interest one be fund B. So the force of interest for simple interest fund A is delta T being equal to R over 1 plus RT, which you've seen before. Now the force of interest for the compound interest is delta T because of ln 1 plus I, which is ln 1.04. So we want to know the value of T where these have the same force of interest. So let's equate their forces of interest. So we'll take the force of interest for A, equate it to the force of interest for B, okay? Now you solve this algebraically, your T now becomes 5.4967. So we realize that which fund will have a higher force of interest thereafter would say that beyond T equals this number of years, the compound interest will have a higher force of interest thereafter. Now let's visualize what we are talking about. We say that for force of interest, simple interest, force of interest, the simple interest reduces over time, but compound interest remains constant. Okay, so we bring the chapter of force of interest to a close, and now we look at an introduction to present value and future value. Present, they all mean exactly as the words mean in common English. Now, present value is the amount of money today that is equivalent to a future payment or stream of payments at a given rate of interest. Okay. But future value is the value of an investment or payment at a specific future time based on a given rate of interest. So if you want to know the relationship between present value and future value, would say that the future value is equal to present value times the accumulation function. And also the present value is equal to the future value divided by the accumulation function. This one, if you apply your algebra, you will get what you need. We've been looking at this all this while. Okay. So this present value is typically what you would, for an investor, typically what the principal, what you go into invest. So what you invest times the accumulation function will give you what you are going to get in the future. That ending value you will get in the future of your investment. So if you invested for 10 years, this is the amount you are putting into the investment. This is what the interest is giving you. And then eventually you end, by the end of 10 years, this is the value of this will be the balance of your investment. Okay. All right. So here's an example. Given that interest is 6%, remember I said we can use either R or I to represent our interest. Given that interest is 6%, calculate the present value of 1 unit to be paid at the end of year 1, at the end of year 5, and then at the end of year 6.5. Okay. So this one, so I have my timeline here. I is 6%. Here is the point 0. This is the present value. This is the point I want to come to. Now, I want to find the value of 1 that will be paid at the end of year 1, at the end of year 5, and at the end of year 6.5. It means that the 1 will be paid here, and there will be another, in the second option, 1 will be paid here. In the third option, 1 will be paid here. Just 1, whether 1 CD, $1, whatever. I want to find the value of this 1 being paid at time 1 at time 0. Again, what's the value of this 1 at time 0? What is the value of this 1 at time 0? Okay. Then the present value, which means that this is the present value. For year 1, is simply 1 divided by 1 plus 0.06, all to the power 1. But because to the power 1, we are ignoring because the 1 is being paid at time 1. And this is what the answer gives us. Now, for the 1 being paid at time 5, you want to know the present value, which is the value at time 0. You simply take the 1 which has been paid, the amount paid, which is 1, and then you divide it by the accumulation function. All right, 1 plus 0.06 all to the power 5, and that gives you this value. Finally, you can do same for 6.5 years, as we have done for the previous two. So for 6.5 years, you see that you are going to, present value is going to be equal to 1, which is paid at time 6.5, divided by 1 plus 0.06, all to the power 6.5, with all of this being the accumulation function. Another example. An insurance policy pays a lump sum of 50,000 in 5 years. If the effective rate of interest is 8%, how much would you pay for this policy today? Today. So we are looking at present value. Okay. Right. So in moving straight to the solution, I have my half times 0, which is my present value today, time 5. Now it says an insurance policy pays a lump sum of 50,000 in 5 years. So the 50,000 will be paid at time 5. Now, if the effective rate of interest I is equal to 8%, how much will you pay for the policy today? How much will you pay here today? So you want to find the present value, okay? So we are saying that present value then is going to be equal to the amount that has been paid at the end of year 5 divided by 1 plus 0.08 all to the power 5. And that's giving us this value, okay? So this is another example for us to better understand the concept of present value. Now, here is another example. A person wants to accumulate 100,000 in 8 years for education expenses. An investment plan offers 8% interest compounded monthly. How much must be invested today? I repeat, a person wants to accumulate 100,000 in 8 years for education expenses. So this person wants to have, this is my timeline, this is my time 0, time 1. This person wants to have 100,000 at time 8. Okay. and he will use it to cater for education expenses. An investment plan is going to offer him 8% of interest, which will be compounded monthly. Now, remember, this is investment is in years, but the interest is being compounded monthly, which means that 8% year is the nominal rate of interest. We can find the effective yearly rates of interest, and then we use it to make our solution quite simple. So we take cue from last week's what we learned, where 1 plus I equals 1 plus I upper M over M all to the power M. Therefore, I equals 1 plus I to the power M over M raised to the power M minus 1. So that I here being equals 1 plus I upper M is 0.08 divided by how many times in a year? 12, because it's being compounded monthly, or raised to the power M, where M is equal to 12. Minus 1, okay? And that's giving us 8.3%. So the effective yearly rate is 8.3%. If that is the case, then the present value, which is the value at time 0, that is how much he must invest today, is this final money he wants to get, 100,000, divided by the accumulation function, which is 1 plus the interest rate, 8.3%, or raised to the power 8, the number of years, okay? So he must put in 52,841.16 today in order to earn 100,000 at the end of 8 years, given that the interest rate is what has been provided. Now let's look at this concept of discount factor, which is going to be widely used in our study. The discount factor, we are using the letter V to represent the discount factor. The discount factor V is the present value of 1 unit due 1 year later. The discount factor V is the present value of 1 unit due 1 year later, okay? So I repeat, it is the present value of 1 unit, and that 1 unit is due a year later. So we have our timeline here, 1 year. So there's one city, let's say 1 city, it is due at this time. What's the present value of this one at the time 0? Okay. And we are saying that we are using V to represent that, which is 1 is what is being paid. So 1 over 1 plus I. Ideally, it would have been 1 plus I, always the power 1. But once it's like this, you can ignore the 1. So eventually we have 1 over 1 plus I, which we are using letter V to represent this function to make it very simple. If V is equal to 1 over 1 plus I, then we see that V of t is equal to 1 over 1 plus I to the power t. Remember I said this is also this to the power t, except that because it's raised to the power 1, we can ignore the 1. So if it's 2, if the time is 2 or 2 years, 3 years, 4 years, you put them in place of the t here. Now, another relationship is that this discount value D, our discount is always equal to the interest times the discount factor. Okay. Yeah, remember I said that discount always brings you here, and then interest takes you here. Okay, that's my simple way of understanding. Therefore, then my discount, if I want to come here, there's going to be that interest that I have multiplied by the discount factor, and that will bring me to my present value. Okay. All right. There are some examples here on discount factor calculations. Problem is that find the sum. Find the sum of the present values of two payments of 1,000 or 100, each to be paid at the end of year 4 and then at the end of year 9. So we have here year 4 and then here year 9. 100 is being paid, 100 is being paid. Okay. So if you look at the question very well, 100 is being paid at time 4, 100 is being paid at the end of year 9. Now you want to find the present value of each of this, then you sum them. Simple. So find the sum of the present value of two payments of 100 each to be paid at the end of year 4, at the end of year 5, or year 9. So 100 being paid here, what's the present value after 0? 100 being paid at time 9, what's the present value? That's at time 0. Sum up their two present values, okay? I think this question is not complete because the interest rate that is involved is not provided. But let's just say that it's been calculated here, okay? So we are working with this interest. This should have been included in the question, but it wasn't. So I'll skip that side. I believe in your notes, it will become a complete question. I'll skip that side. We're using this as our interest. So the present value of 100 being paid at time 4. It is that 100 has been paid all over the accumulation function, which is 1 plus the interest all raised to the power 4. And that gives us this. Then the present value at time 9 is 100 over 1 plus 0.0816 all to the power 9, which is this. So to know the right, so to know the present values, you simply sum them. So we'll take the present value of their total. We'll take the present value of their total and we'll sum this 73.07 plus 49.36. Okay. All right. Okay. So in effect, what we will say is that if we've spoken about present value, so the reverse actions will give us the future value. Okay. Right. So if you want to talk about the future value, I have an investment here. This is future value. At time 0, I go to put in an amount P. I want the money back in 5 years' time. So whatever the value of P is at time 5 is my future value. So usually you will take the P, whatever has been invested, you multiply it by the accumulation function, and then that will give you the future value. Now we want to talk about the concept of equation of value. Now the equation of value is a mathematical representation of the equivalence between cash inflows and outflows over time, which has been adjusted for the time value of money. So as in our formula, we are saying that P, for the formula is P is equal to the summation of Cj, where J is running from 0 to N. We'll define C subscript J as the cash flow at time J. And then VJ is the discount factor for the J periods. P is the present value. F is the future value. So generally, the present value is equal to all the cash flows that have happened over the period multiplied by their own discount factors. Okay. And that will give us what we want. So by means of expansion, I'm trying to expand this. P here is our present value. That's what the point here. So J is running from 0 to N. Let me say my N is equal to 5. So J is running from 0, 1, 2, 3, 4, and then 5. Now there's some cash flow. So there's C1, C2, C3, C4, C5. So to know the present value, I'll multiply my C1 by the V, my discount factor to the power 1. And then, no, this, okay, so this is C1 comes here to become CV1, C1V1. C2 comes here to become C2V2, and then on for the rest. So to find the present value, I'm simply going to add my C1V1 plus C2V2 plus C3V3 plus all the way to the last term. That's what we have. So CJ is VJ, J summing, this is summation symbol, okay, running from 0 to N, whatever time that we are looking at. So how do we apply the equation of value then? Let's look at a problem. A loan is repaid with 2 payments. The first thing is that there is a loan. Now this loan is being repaid with 2 payments, 1,000 cedis after 1 year, and then 1,002 after 2 years. Now find the present value if the interest rate is 5%. I will always draw a timeline. So I have my timeline here. This is where I am today. But this loan will be paid after year 1 with 1,000. Then after year 2, we'll pay 1,002. So I've taken a loan, okay. I'll pay 1,000 after year 1, 1,002 after year 2. The interest involved is 5%. I want to find the present value if the interest rate is 5%. So what do? This 1,000, I must discount it to come here. This 2,000, I must discount it to come here. Then I sum their discounts. So the first one, present value of the first one, I have 1,000 divided by 1 plus R, which is the interest, raised to the power 1, which is the time, okay? And I'm getting this. For the second one, I have the amounts 1,002 divided by the accumulation function, 1 plus R, all raised to the power 2. And that's giving us this. So to find the present value of total present value, I simply sum PV1 plus PV2, and that gives me this. Another example, how long will it take for 100 cedis to accumulate to 300 if interest is compounded quarterly at the nominal rate of interest 6% per year? So let's know the quarterly rate, which is 0.06 divided by 4, 0.015. Now, let me draw my timeline as usual. Okay, so let me draw my timeline. How long? So I'm looking for time. So I have 0 here, I have T. How long will it take for 100 invested now to accumulate to 300 at time T if the interest rate is 6% compounded yearly? So compounded quarterly. So if I want to know the quarterly rate, that's what I did here, 0.06 divided by 4, which is 0.015. So by equation of value, then this my T here is not years, so this my T here is number of quarters, because I'm going to use this quarterly rate. So pen my representation, this is my future value. So my future value, which is 300, is equal to my present value times my accumulation function, okay? All right, so given this, if you apply your, in this case, let me erase this one, and then we can divide both sides by 100, and that's going to give us 3 is equal to 1.015 n. In this case, I can take log of both sides, and that's getting me n, then the log of 1.015 all over log of 3. Okay, so therefore, then I divide both sides by log of 1.015, log of 1.015, then n stands the loan. So that's what we have here. N being equal to what is here? Log of 3 over log of 1.015, and that's given us 73.79 quarters. Remember, I said that T is quarters. So you can change it to years. So 73.79 quarters will give you how many years? There are 4 quarters in a particular year. So you can just divide this by 4, and you should get about 18.45 years. All right. Okay. Now, the key point when it comes to equation of value is that the equation of value can be used to solve for the rate of interest I, okay? That will balance the cash flows. So a student takes 15,000 loan to be repaid with 7,000 in year 1 and then 8,005 in year 2. Find the effective rate of interest. So let's say the loan is, I'll draw my timeline again. The loan is being taken now, so 15,000 at time 0. You will pay at the end of 1 year, you pay 7,000, a portion of it. Then at the end of year 2, you pay 8,500. What is the effective rate of interest? My expectation is that this 15,000, which is my present value, my expectation is that this 15,000 should be equal to 7,000. Discount this, they should be equal to the sum of this plus this discounted time here, it should be equal to this, okay? So 7,000 times, I don't know what my interest, so I'll use V to the power 1 plus 8,500 V to the power 2. So I can use quadratic equations to solve for V. Whatever value I get for V, remember V is equal to 1 over 1 plus I. So whatever value I get for V, I fix it here and I equate it to 1 over 1 plus I. Then if I apply algebra, I can get I being equal to a particular value. What are some of the ways that we can use the equation of value? You can use it to do for loan repayment schedules, bond pricing, investment comparisons, and so on. So the equation of value just ensures that there's equivalence, okay, by adjusting for the time value of money. You consider time, you consider interest. So with the concept of equation of value, if let's say you know that in the next 5 years, you want to, for example, marry, okay, you want to marry, and you know that you will need 100,000 Ghana cedis for your wedding, you will be ask yourself, so if I need 100,000 Ghana cedis for my wedding in 5 years' time, and I want to do an investment, given that the interest rate is, let's say, 5%, how much should I put into the bank today so that to ensure that I get my 100,000 in the next 5 years? So you apply the equation of value, and that will help you figure out how much to put in today. So here's an exercise for your practice.